I am Jamie West, and I'm part of the yellow team along with Jay and Joel. I'm part of the spray booth pressure station. And in this project, or this presentation, I'm going to tell you about the steady state operating curve, what we did with the step modeling, the frequency response, and then the frequency response modeling. Here's the schematic of our system. It's got a motor powering a blower, which controls the pressure in each booth, I believe, and that sends signals to a computer, which sends results. Okay. The block diagram is this. The input is the motor power. The transfer function is the motor. The system is the electric motor fan, and the output is pressure in centimeters of water. In the first experiment that we did was we put in a power, and we got a percentage of pressure, and we used this to obtain a steady state curve in which I was to do pressure from 1 to 15 centimeters of water. Joel was to do 15 to 30, and Jay was to do 30 to 45 centimeters of water, respectively. Then we did the step-up experiment, and we do this experiment to get system gain by dividing delta C divided by delta N. We also can get dead time and tau from this experiment. Then you can do step down and gather those same values, but for the step down. And here are the tau values for the step up and step down, and even the modeling for the step experiment. We realize that there's no negative values for those, but I've overlooked them. There's big uncertainties in the step down in the first range, and that's weird. The gain values for the step up and step down and the modeling were pretty consistent in each range. The dead time values in the first range on the step up was the uncertainty was pretty big, but the rest were pretty consistent. In the model equation, this was find the model equation for the step experiment that we did. We used tau, or a total time was 15 seconds time delay for the experiment to start. The amplitude was 20%. The gain was 0.75 centimeters of water per percentage, and the dead time was 0.4 seconds, and the tau was 1.5 seconds. Okay, the next experiment that we did was the frequency response experiment, which we first did a sine wave, which from this we can get a delta M and a delta T, or a T, and with these we can get values to ascertain a Bode plot. Here's an example at frequency 0.2 hertz. we got, for this one, we got the amplitude ratio is 0.39 centimeters of water, and the phase angle was negative 14.4. Here's the Bodie plot for the first range. FU was 0.05 cycles per second. The K was 0.37 centimeters of water per percentage. The 1 over KCU was 0.2 centimeters of water per percentage, and the order was 0.21, but that could be off by power of 10. Not sure. The phase angle versus frequency looks weird, but that's just the value that I got. For the Bodie plot for the second range, it looked pretty good. The orders was 0.85, and the K was 1 centimeter of water. The second range and the third range, they look pretty consistent. They looked a lot alike. Okay. The modeling for the frequency versus AR in the range 1 was the actual experiment was pretty consistent with the model. The experiment in the phase angle versus frequency in the experiment was off. In the second range, the amplitude versus frequency Bodie plot for modeling was pretty consistent with the modeling, and except for the last point over there, it was an outlier. Okay, conclusion. I talked about the steady state operating curve and why we did it and what we gained from doing that experiment. We got the system gain, the tau, the dead time. Also, we did the frequency response, and from that we could put together a Bodie plot, which we got